for iOS development, you encounter a bunch of these diagrams with two columns and a bunch of arrows connecting them. Well, these are the visual depiction of what happens when an iOS application loads, runs, and then terminates, the so-called life cycle of the application. Notice how they are laid out chronologically, since there is a predictable order to the events that occur during the execution of all iOS applications. Why do we care? Well, understanding the application lifecycle is very helpful for the following reasons. 1, to understand the manner in which the operating system interacts with our program, often in ways we don't see and don't have much control over. 2, to help us to understand how the various files in an Xcode project come together to form an executable program, which is quite helpful when you are first looking at an iOS project and trying to figure out how it works. And 3, to help us to know where to place our code within the overall project layout so that it will interact correctly with the operating system and the frameworks. Let's start by tracing through the sequence of events that happen at launch time, that is, when the user clicks on our application's icon to start the program. The first thing that the OS needs to do is to find the program, which should be on the device's hard drive in a .app directory with the same name as the program. This is called the application's main bundle, and within the main bundle, the OS will find and load into RAM memory the app's binary file, which contains a combination of the program's data and instructions for what to do with those data. It will then begin executing those instructions, starting with whatever is found within the main function. The important line here is the call to the UI application main function, which is part of the iOS's UIKit framework code, which is assumed to have been loaded already into the memory by the OS before our program even tries to run. This function creates the UI application object, the master object for the entire application, and turns control over to it, but not before designating some object within our code as the application's delegate, the purpose of which we will discuss later. This can be designated by name as the last argument of the UI application main function, or, if that is left nil, then it will be designated within the nib file, which loads as follows. Around the same time as the OS is executing the main function, it also finds and reads the application's info.plist file, which is an XML manifest file that contains, among other things, the name of the app's main nib file, generally mainwindow.nib. This nib file, which is another binary file, distinct from the application's binary file, will then also be loaded into memory and utilized by the master UI application object. When the nib loads, all the objects it contains, as depicted in Interface Builder by the icons here in this sidebar, will be created, that is, instantiated, along with any connections they might need to make with other objects in the project. Every nib must have a connection to its files owner object, which is the object that created and thus owns the nib. Notice that the symbol for it is semi-transparent. This is because the nib file doesn't create the instance of the object that owns it. That would be impossible. It just maintains a placeholder for its connections, a so-called proxy object. In this case, the file's owner is the master UI application object. On the other hand, the appDelegate object is created by this nib file, and thus its symbol is solid. Notice that this is where the application's delegate object is specified, by this connection between UI application and the appDelegate class. The role of the delegate is to act as the connection point between our code and the UIKit framework code. In terms of objects, we would say that the UI application master object preferentially communicates with the designated delegate object by sending it messages that the delegate can optionally respond to by implementing the appropriate override method. An example would be when the application has been fully loaded into memory, at which point the UI application object sends out the application did finish launching message, which the appDelegate responds to in this method, making use of a connection that was made in the nib between it and a window object to tell that window to make itself visible. So we can depict the launch sequence like this. Info.plist loads mainwindow.nib, the main function instantiates UI application, which has a proxy in the nib, UI application delegates to the appDelegate object, which tells the window object in the nib to become visible. Control is then returned to the UI application object. The important thing to observe here is that there are only two places that a developer can break into the launch process with their own custom code, the nib and the appDelegate. Any object that you create will have to have a direct link back to one of these two classes. The other way to look at this would be to say that there are a total of three sources of binary code in an iOS application. The Apple-supplied framework code, such as UIKit, Foundation, and Core Graphics, your application's binary file, which contains compiled versions of the project's source code files, and your nib file, or files, which are the compiled versions of the project's .zib files. Now after launch is complete, UI application just goes into what is called the event loop which consists of waiting around to be informed by the OS that some event has occurred, typically in the form of some user touch input, at which point UI application sends out an event message to our code, which has a chance to respond provided something was created in either the nib or the app delegate that is capable of responding. We won't get into it here, but the capacity to respond to an event requires that an object is a subclass of UI responder, which includes all of the UI view subclasses and UI kit controls like buttons, sliders, tab bars, etc. Anyway, after the event response is finished, control returns to UI application, which goes back to processing the event loop. The final phase of an application's lifecycle is what happens when the user attempts to exit the program. With iOS 4.0 and later, that is, since the introduction of multitasking, the app may enter the background state or terminate fully. The app delegate is again involved as it receives messages from UI application. So that is a quick review of the iOS application lifecycle. Now let's consider the typical iOS project layout and where to put our code. We know that all objects must be created by either the main nib, the app delegate, or by an object that was created by one of those two objects. Yet this isn't enough to help us decide where to put our code. Instead, we have to consider the full application lifecycle and organize our code accordingly by separating it into distinct beginning, middle, and ending sections. The beginning will always be where we initialize our application and get it ready to run. The middle will be where it actually runs, and the end will be where we clean up and possibly save some data before exiting. The programmer has to decide at which point to perform each of the application's essential functions, though in most cases it is fairly obvious. Anything that is used when the application first starts belongs in the launch code, while anything that changes during the running of the app is dealt with in the run portion of the code. If you aren't sure, put it in the launch code. For instance, let's take a look at the Tickless Chicken application, which we built in a different video. Here we'll focus on the project layout, why the code is where it is within the project. In this case, the nib file creates the app delegate and the main window. Then the app delegate creates and displays a UI view subclass called main view in the main window. Almost all applications will create at least one UI view subclass at startup, if for no other reason than to guarantee that something is there to respond when UI application sends out an event message. A UI view subclass is also a great way to get something to appear on the screen. When a UI view subclass is created programmatically, that is, from within the code, the initWithFrame method will be called. If it is created from a nib, it would be initWithCoder. This is where the background color is set, a holder view for the images is created, the image data are loaded into arrays, the image holder is displayed, and the laughing sound data file is loaded into memory. Then control is returned to UI application, which goes into the event loop. Whenever the user touches the screen, the event loop sends out a message which the main view object will receive and respond to by overriding the appropriate method. The shutdown code consists of a couple dealloc methods in the app delegate and the main view classes. As is often the case, most of the code in this app could only possibly go in one place, though there are two areas where we have some decisions to make. The first is in whether to load our objects from the nib or from the app delegate, and the other has to do with when is the best time to load our image and audio data into the memory. As to the question of whether it is preferable to load objects from the main nib file or from the app delegate's app.did.finish launching method, the choice is up to you. Certainly the nib is better for laying out the positions of visible objects in the interface, so if you are making something like a settings menu, the nib would be a good choice. On the other hand, connecting the source code to a nib file requires the use of IB outlets and IB actions, which can make the code harder to read. The running application doesn't care how the binary was created, so these choices are for our benefit only. You have to decide for yourself which will be easier later on, to find all of the hidden connections between a nib file and the source code, or to wade through source code that is filled with code that could have been generated automatically in Interface Builder. As to the question of when is the best time to load assets, whether that be image data, audio data, numerical or textual data from a database, whatever, programmers constantly need to strike the right balance between the time it takes for the processor to move data around and the brisk responses that users expect when they click or touch something on the screen. On the one hand, you can try to front-load your program by loading as much as you possibly can at startup, so that when it comes time to respond to user input, your program doesn't have to go off and move a bunch of data into the memory before it can make that happen. On the other hand, you may want to defer the loading of some of the application's data or resources until the moment that they are actually needed, so-called lazy loading. This is a technique that is used throughout all of computer programming, but it is particularly relevant to asset loading, since it is possible to run out of memory space and force the program to stall at an inopportune moment while it performs a data swap. The answer in this case, however, is pretty obvious, since the whole point of the app is to see the chicken react to being touched. Thus it makes sense to load the image and sound data at startup rather than waiting for the first touch event to occur. Okay, so now we should be able to open up any Xcode project and figure out how it works. Let's test our skills on some of Apple's sample code. Let's start with UI Catalog, which displays a table view that allows you to see samples of all of the different UIKit control classes in action. Now, when you first open up this sample code and see that there are dozens of files here, you might be overwhelmed and sit there going for several minutes. Okay, maybe not, but it is a complicated project. So let's use what we've just spoken about and try to figure out how that initial screen gets loaded and the table view gets populated. The approach to analyzing it is as follows. Find the main function and check that the call to UI application main has not been tampered with, specifically the last argument, which should be nil, and it is. So next we go to the info.plist file to find out the name of the application's main nib file. In this case it is main window, which it usually is, so that's loaded next. So find mainwindow.zib, usually under resources, click once to open it in Interface Builder, make sure that the right utilities sidebar is showing and is set to the Identity Inspector tab, the little Transformers icon. Notice that Interface Builder always displays a list of the objects that a nib contains over here on the left, with the top one being the file's owner, UI application. Right-click on that to see if it makes a delegate connection, and indeed it does, to the AppDelegate class. So move down the list to the AppDelegate object, click on it, and look over in the inspector to see the corresponding source code file, which is also called AppDelegate. Now click on this little arrow to the right of the class name to go to that file. Okay, so this is the header file, not very useful. So click on the name up here and navigate to the .m file. And here we find the application did finish launching method override that we would expect to find. So what does it do? Well, it looks like it just loads this navigation controller's view. But in order to do that, this navigation controller must already exist. But I don't see it being instantiated anywhere here in the AppDelegate. Since no other files have been loaded yet, we know that it must have been created in the nib. So hit this left arrowhead a couple times to go back there, and sure enough, here it is, the navigation controller object. Click on this disclosure triangle at the bottom here to open up the list view. It's the only way to see what other objects are in here. And use the other disclosure triangles to expand the list. Now we see that this thing is loading a nav bar, another view controller, and a table view, basically our entire UI. Click on the main view controller, hit the arrow in the circle to go to the source code, switch to the .m file, and here we have it. In the viewDidLoad method, this is where the entire table view is being populated. So it turns out that this rather complicated looking project loads from a nib and an AppDelegate like any other. Let's try that again with a sample code for the MoveMe app, which builds this app that has this moving placard in it. So main function, UI application main has not been tampered with. So info.plist, main window, there is a delegate connection made. So go to MoveMe AppDelegate, look at the .m file, application did finish launching, and okay. So this is programmatically creating a view controller and displaying its view. But notice that this is passing the creation of its view to this MoveMe view nib file. So open that, go to its view object, and then go to the source code class for that view object, and look for the entry point. In the case of UI view, this would be a init with coder since it is instantiated from the nib. And it looks like it calls this setUpPlacardView method, which creates an instance of the PlacardView class. Looking at the PlacardView.m file, we find that it loads an image that represents the placard shape, and it overlays the text on top of it. And that is how we get to the initial screen of the app. Now you may be wondering, why did they create this seemingly unnecessary view controller? Let's try loading the MoveMe view directly and see what happens. And we see that it loads, but with a white background. So that must be what the nib is for, to allow the developer to set the background color visually. And that also explains why you need the view controller to load the nib file correctly.